there's a remote or something, then I also connect.
Yeah. All right. Perfect.
I mean, it's okay. A few minutes is. This one? Yeah, test. 1, 2, 3. Okay. Mm, This much? Okay. Can you hear me now? Clear? Okay. Sure, sure. I got the internet and all working, so. No problem.
9:59. Okay. And then your talk's already ready to go, right? I think it's morning folder. I might even just open it up now. Gyrotrons. Yeah, I'll just open up his. Okay. Let's get the thing going here. Let's see. Is it on? Check. Check. How do you turn it on? Is there a switch? Is there a switch? Check. Not on? I mean, well, I don't know if this is going to be able to be replaceable. It's too thick. Okay, this is for the, okay. So, this is the live stream, and this is the, check. Channel 6, no? Check, okay, I turn it on. Okay, let's go on. Check. Check. It was on. It was on during our test. Check. All right. Well, I think we should get started. My name is Michael. I'm here with Somil and there's Chris. Welcome to the NCC AVS annual equipment exhibition, which is going on next door, and the technical symposium, which we're going to kick off, and a student poster session. So all three events are occurring in conjunction. This morning, we're going to have a swap because the first speaker is still stuck in traffic. So I'm going to introduce the second speaker who is going to go first, and I have the pleasure and thank you to Somil who put together the bio. Monica Blank received her MS and PhD from MIT. In 1999, she joined CPII, where she works on high-power millimeter wave gyrotron amplifiers and oscillators. And since then, she's received multiple awards, and we're honored to have her today to talk about gyrotrons for magnetic confinement, fusion heating, and she's going to go first. So let's welcome our first speaker. Yes, thank you. Yes, so. Oh, yeah, there you go. Yes, sorry, thank you.
Great, thank you. Thanks so much for allowing me to be here today. I really appreciate it. So what am I going to do? Okay, and I don't use this one? You need both? Okay, that's really weird. Okay, let's go full screen. Yeah, we're good. No, I don't need that. Perfect. Thanks a lot. So probably the title of the talk is really mysterious, but we'll get into it, don't worry. So we can start with some fusion basics. I think people know what fusion is, but let's all get on the same page. Then I'll talk about plasma heating methods. And deep into the talk will be the first time that I really mention gyrotrons, which is sort of an esoteric subject, but I hope to give you some background on it, and then I'll summarize. So fusion basics. I think people know what nuclear fusion is, but it's when two light nuclei, usually deuterium and tritium, combine to form a heavier nuclei, usually helium, and neutrons and a massive amount of energy come out. So there's many kinds of fusion. Most famously, I think the sun and other stars power themselves with fusion. So on the sun, it's a proton-proton fusion, and the internet tells me that 620 million metric tons of hydrogen is turned into 616 million metric tons of helium each second on the sun. I guess that sounds about right, I don't know. But also, we want to achieve fusion on Earth as a way to generate power as opposed to oil or coal or wind or solar or anything like that. So there are two distinctly different kinds of fusion. There's probably more kinds, but there's two main kinds of ways to create fusion on Earth. inertial confinement and magnetic confinement. So inertial confinement fusion across the way at NIF, the National Ignition Facility at Lawrence Livermore Lab, 2 years ago, they had a really big result. This was reported in the New York Times and everywhere else, that the headline says, scientists achieved nuclear fusion breakthrough with blast of 192 lasers. And what they did in December of 2022 was they got more fusion energy out than they put in to make the fusion reaction happen. So that's called ignition, or break even or burn, whatever you want to call it. And they achieved this goal about 2 years ago. It's a massive goal. So I'm not an inertial confinement fusion expert. I'm actually probably not any kind of expert, but I can explain it easily with a cartoon. So in inertial confinement fusion, there's a fuel cell, let's say a ball of deuterium and tritium, and it's contained in a little vessel that they call a Hallroom. I don't know why. And it's really small. The dimensions are there. It's 1 centimeter by a half centimeter. So in this tiny little Hallroom with the fuel inside, you train 192 lasers, high power lasers. And so everything heats up, and there's a bath of electrons, and the outer layer of the fuel ablates at really high pressure, 150 megapascal, and then the fuel accelerates, compresses or accelerates inward, implodes, I would say, and that's what enables the fusion to occur. So it's really tiny where it's happening, but of course the facility is massive. So this is an internet photo of the National Ignition Facility at Livermore. So all those 192 lasers and all the infrastructure you need make it really big. So NIF had this wonderful achievement, and they should feel really proud. But what's not always reported in the New York Times is this ignition that they achieved occurred for a tiny fraction of a second. So while it's scientifically extremely important and it's a good step, they're not very close to putting power on the PG&E grid. So there's another kind of fusion, the kind that I work in, which I think, you can humor me, I think is a lot closer to putting power in the grid. Probably neither one is too close, but we can pretend for the next 20 minutes that this one is. So there's a completely different way of making fusion happen on Earth called magnetic confinement fusion. And in magnetic confinement fusion, you create a plasma of the fuel, deuterium and tritium, and you contain this plasma with strong magnetic fields. So this donut-like plasma-holding thing is called a tokamak, and there are other variations on it, but the tokamak is the most popular right now. And you use very complex magnetic fields. There's magnetic fields going around, which create a magnetic field around the donut, and then there's the center poloidal magnetic fields, which make the magnetic field that way, and you need that because you have to keep that plasma in there somehow when you're heating it up hot enough to make the fusion reaction. So magnetic confinement fusion also has its records. Just last month at the East Tokamak in Hefei, China, they achieved a world record of confining a dense plasma for over 1,000 seconds, which is 15 minutes or so. So they did not achieve break even or ignition with that shot, but just like ignition is important, so is the ability to contain it. Obviously, if you're going to put power on the grid, you kind of need this to be happening all the time, not just for a few fractions of a second or even 1,000 seconds. You need it to happen all the time. So there are records also, and I think that most people, maybe except for those that work at National Ignition Facility, think that magnetic confinement fusion is maybe a little bit more likely to put power on the grid in the next few years or decades. So the big flagship magnetic confinement fusion device is ITER, the International Thermonuclear Experimental Reactor, which is being built in France, and it's a multinational thing. So it, like NIF, is massive. It's 23,000 metric tons. The major radius of the tokamak is 6.2 meters. It operates at 6 Tesla, and the plasma volume will be over 800 meters cubed. And the whole secret to fusion in magnetic confinement fusion, much like inertial confinement, is you got to get it hot. So they have to get the plasma to 150 million degrees, And they're going to do that with a variety of heating techniques. So just to continue with what you need for fusion, you really need four main things. You need a plasma, which is your fuel. You need to have confinement, which is achieved with the magnetic fields. You need a really high temperature, over 100 million, so that the nuclei can overcome their repulsive forces and actually fuse. And then, yay, AVS, you need a vacuum, because you can't have just any old thing in your plasma. You have to have a good vacuum first so that you can put in the deuterium, tritium, whatever you're trying to make your plasma out of. So where I come in is in the heating. So I still haven't mentioned the word gyrotron yet, even though that's what I work on. We're halfway through this talk, but I come in on the heating side. So for magnetic confinement fusion, there's several different heating methods, and the one that I work on, is much better than the others, and you have to believe me because nobody's here to call me a liar. So I don't want to get too much into the details, but there's all different kinds of heating. So there are three different RF kinds of heating: a very low frequency ion cyclotron resonance, where you heat up the plasma by making RF resonant with the ions, and that happens at 40 or 50 megahertz, very low frequency in most tokamaks. There's something called lower hybrid heating, which is a reference to a plasma wave situation, and that happens at the low number of gigahertz, like 2, 5, 10, 8 gigahertz, something like that. Neutral beam is a way of heating that doesn't involve microwaves at all, so I don't care about that one. And then what I work on is electron cyclotron resonance heating. So unlike ion cyclotron, here the RF is interacting with the electrons in the plasma to heat everything up. And that happens usually for most modern tokamaks between 30 and 300 gigahertz, depending on the specific magnetic field of the tokamak. And it has a lot of advantages over other kinds of heating. So whatever kind of heating you use, you have to get your energy into the tokamak. And the tokamak is a very complex thing. So one advantage of electron cyclotron resonance heating is small port size. So you can put a megawatt CW of power into the tokamak in a hole that's just 2 or 3 inches in diameter. It has excellent heating efficiency. Also, in addition to heating the plasma, you're trying to control it a little bit. So with electron cyclotron, you can really steer and control plasma. And it works for very high density plasmas. There's all these complications of waves in plasmas. So recently, in the last, say, 10 or 20 years, electron cyclotron resonance heating has gone from being one of the ways that tokamaks heat things to the main way. So for example, ITER plans to have almost 70 megawatts of electron cyclotron resonance heating, only 20 megawatts of ion cyclotron, and 33 of neutral beam. And tokamaks that are designed more recently than ITER, some of them are all electron cyclotron resonance heating. It has emerged as the best way. So what the heck is that, electron cyclotron resonance heating? Well, I'm not going to get into the plasma details, but I can get into the hardware. So most tokamaks are large, and they're in a building somewhere. Then in another building, 50, 100 meters away, they house a large number of devices called gyrotrons. It's first mention of gyrotron already, 14 slides in. And a gyrotron, which I'll describe a little bit later, there will be 5, 10, 15 gyrotrons, and each individual one has a waveguide. Each one is making approximately a megawatt of CW power at the frequency that's demanded. And then transmission lines carry this generated RF power into the tokamak, and through small ports, it's injected and heats. So in real life, a small facility in Lausanne, Switzerland, it looks kind of like this. So I don't think anyone could pick the gyrotrons out in this picture, but I can. These cylinders, these yellow and gold-colored cylinders are the gyrotrons, each one sitting in a superconducting magnet. And so all of this is connected by a system of corrugated waveguide transmission lines to the tokamak, which is quite a distance away, because even worse than trying to find housing in Silicon Valley, space is at a premium at a tokamak facility. There's a lot of stuff, and it's a excellent feature of electron cyclotron resonance heating and gyrotrons that they can be located remotely. Okay, so let's get into gyrotron a little bit. Gyrotron is sort of a mysterious device, even for people who work on vacuum electron devices. It is a vacuum electron device. It's a close cousin, maybe an attractive younger brother to the magnetron or klystron devices that you would have heard of. And the deal is that it is uniquely capable of making megawatt power and more in the high gigahertz range. Say 30 to 200 gigahertz is where a gyrotron is most happy. So interestingly, the idea was conceived in the 1950s, and first experiments were in the 1960s, and it was literally invented for this, for fusion plasma heating. Since then, many applications have grown up, but in the beginning, it was all about a tokamak, all about fusion. Okay, all vacuum electron devices are the same. So people haven't heard of a gyrotron, but you've probably heard of a magnetron or klystron. And they all have the same elements. And those elements are a source of electrons, which we call a gun. This is always a problem when you're shipping something. What's in the box? A gun? They're like, what? I don't know why. We shouldn't use violent names, but it is an electron gun because a vacuum electron device, it's not solid state. It works with free electrons. Then somehow you have to have a space for the electrons and the electromagnetic wave that you're trying to amplify. That's got to have a space to interact. So we have some type of cavity or interaction region. Then it's not perfectly efficient. So you've got this beam of electrons and they gave up their energy to the wave, but you still have a lot of electrons, energetic electrons left. So you have to have some area to safely collect that. And again, yay, AVS, we're vacuum electron devices, so we always have to have a vacuum, which means you need a vacuum window. After you've made all this RF, you have to get it out while still preserving the vacuum. So in gyrotrons, we use chemical vapor deposition diamond. Other ceramics are used, like beryllium oxide or alumina, Al2O3. But okay. Every vacuum electron device has these basic elements, and what separates them, what makes a gyrotron different from a klystron, a magnetron, a helix, TWT, is this circled in green, the space for the electrons and the electromagnetic wave to interact. That's the main thing that makes them different. And that's because you have to achieve some type of resonance. So I always use a surfing example. So in this, I guess the surfer is actually the particle and the wave is the electromagnetic wave. But if you sit out in the ocean on your surfboard and you're not paddling, then the wave goes by and you just bob up and down. If you want to catch the wave, you actually have to paddle, 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 like on the right, and try to match your velocity to the velocity of the wave, and then you can exchange the energy. So on the right, the guy's paddling, he'll match his velocity, and he'll ride the wave in. That's exactly how it happens in a vacuum electron device. Or a particle accelerator is the opposite. We're the opposite of a particle accelerator. We want the electrons to give the wave energy. In an accelerator, the wave is giving the electrons energy. And actually, the surfing example, I think, is more like an accelerator, because the surfer would be the electron, but whatever. So each individual device, gyrotron, magnetron, whatever, you have to have a way to make that phase velocity matching and energy exchange happen, because the electromagnetic wave is traveling at the speed of light and the electron beam is not. So I will not get into details, it is way too boring, but each device has a specific physics method to make that exchange happen. And the gyrotron does it with a magnetic field. So other devices tend to use the walls of the interaction structure to slow the wave down and create the resonance. A gyrotron doesn't use the walls at all. It simply uses the magnetic field. The magnetic field spins the electrons up at the cyclotron frequency, which is 28 gigahertz per Tesla, and then the electrons are sitting there waiting to give their energy up. So if you wanted to make a 280 gigahertz gyrotron, you have a 10 Tesla magnet, and I can assure you the gyrotron interaction is strong. If you have a pipe, a beam of electrons, and a strong magnetic field, you will get a gyrotron interaction every time. Might not be the one you want, but it's there. So because the gyrotron doesn't use the walls of the circuit, there's a divorce between the size, the physical size of the interaction structure and the frequency. This is a link in a klystron or a magnetron that is hard to break. So what happens is, as the frequency goes up, the wavelength is going down, and if your circuit size is 1 or 2 or 5 wavelengths, it's getting small, 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 small. And if you can only cool, say, 2 kilowatts per square centimeter, and you're running out of square centimeters, then the frequency drops off. So say a magnetron or a klystron can make tons of power at 1 or 2 gigahertz, but by 30 gigahertz, they're making nothing. And this is where the gyrotron comes in. So without a single equation, just pictorially, I can show you the gyrotron's secret weapon, which is higher order modes. So this slide has, to scale, the interaction circuits for 3 gyrotrons that my company sells. Every single one of them is at 94 gigahertz. So on the left, we sell a 94 gigahertz gyrotron that makes 10 kilowatts power, and it operates in a low order mode. The RF is indicated there. The red is the high field, electromagnetic field region. So it's a donut. And the interaction circuit radius is about 2 millimeters. In the center, we also sell a 100 kilowatt gyrotron at 94 gigahertz. And its circuit size, just by choosing a different mode, we have a much bigger circuit, twice as big. Its radius is about 0.35. And then what looks like stained glass on the right is actually something we call the 22-6 mode. So there are 6 radial variations, and there are 44 variations around the azimuth. And the red circle on the right indicates the region of high electromagnetic field where you would put your electron beam. And that's a megawatt 94 gigahertz gyrotron that operates in the 22-6 mode. So we've broken the link. So if you want to go to higher frequency, you don't need to have your circuit scaling down. So I say it like it's so easy. There is no free lunch. There are problems with going to higher order modes. But in general, the gyrotron frequency is dictated by the magnetic field. It's not dictated by the circuit size at all. And it's always funny for me walking around our factory, because for most devices, you can see, if I'm looking at a klystron, I can say, oh yeah, that's 35 gigahertz, that's 10 gigahertz by the waveguide size. A gyrotron, you have no idea what the frequency is. Someone has to tell you what the magnetic field is. But this is the gyrotron's secret weapon, and this is why at 100, 200 gigahertz, the gyrotron can make a megawatt and other devices can't. Because when we want to go up in power, and we can only cool 2 kilowatts per square centimeter, we just go up in square centimeter, and that's how we do it. It's not quite that easy, but we can pretend for now. So in cartoon form, a gyrotron is like every other vacuum electron device. At the bottom, we have a cathode, which for us is a ring. We're making a hollow beam for reasons that don't matter too much. Then we always have a superconducting magnet. We sit in a superconducting magnet. The role of the magnet is also very different for a gyrotron. In a klystron or something, it's to sort of guide the electron beam. For us, it's our entire interaction is from the magnet, so it's very important. And because it is 28 gigahertz per Tesla, about the cyclotron frequency, if you want a high frequency gyrotron like 170 gigahertz for ITER, that's a 6 Tesla magnet, so it's always superconducting with a large bore. We are operating in these funny modes I showed you, so we have to convert that inside. If you tried to exit the gyrotron in the 22-6 mode, no one can do anything with that stained glass looking, hollow power. So we convert to a Gaussian beam and exit the side out a window, which for us is CVD diamond. And then the electron beam, which is indicated in white, continues on to the collector, which is usually huge, and it's safely dissipated out there. So moving from cartoon to solid model, on the right is what a gyrotron sort of looks like. So down at the bottom is our electron gun. We have an area where between the gun and our interaction where the electron beam is being compressed by the magnetic field. The gyrotron sits in its superconducting magnet, and the cavity, the interaction space, is right at the high field region, right in the middle of the magnet. We've got some mode converter, and then this is a little bit more realistic. It indicates that the collector is the single biggest part of the gyrotron, because we're about 50-ish% efficient. So to make a megawatt gyrotron, you've got a whole other megawatt of electron beam that has to be safely dissipated somewhere. And that's also easier said than done. But some typical parameters for us, This gyrotron shown here operates at 140 gigahertz, 1 megawatt. The customer spec was 1800 seconds, which is about 30 minutes, I guess. And we operate usually 80 to 85 kilovolts and 45 amps or so. And we have to come out in a Gaussian beam and be pure. So getting a little bit more realistic, oops, I skipped one. Oh, somehow. I don't know what happened to that other slide. I had a picture of a gyrotron, but here's another good one in test. So the superconducting magnet is that silver thing with jail bars on it. And in this case, it's about a 5 Tesla superconducting magnet. And then the gyrotron's up above. So we're looking down sort of, that's the CVD diamond window on the conflat flange there. And the collector is everything up above. And then I have some typical measured data. This was supposed to be a 1.5 megawatt gyrotron, and it was. We have output power on the vertical axis and voltage, cathode voltage on the horizontal. And so if you change the voltage, the gyrotron actually is infinitely tunable in power. Our customers often ask us, can we get less power? And I tell them, oh yeah, like if you go down to 0, I'll give you a discount even. So the gyrotron naturally you can vary power from full to 0 by changing a variety of parameters, but cathode voltage is one of them. And you can see on this, we achieved our goal. We were above 1.6 megawatts, and we did that with 60 amps cathode current. So I don't really want to get into the gyrotron physics, but we've had a lot of progress. My company shipped its first gyrotrons in 1977 to the Elmo Bumpy Taurus at Oak Ridge National Lab. That sounds like a cartoon character, but it is in fact a fusion device. And so we're about 50 years in. Gyrotrons were invented in Russia. They're about 60 years in or more, and a lot has changed. So I'm pretty old, and when I was at MIT, superconducting magnets were really just coming online. And we used Bitter magnets, a copper magnet that was perfected by Francis Bitter, the great Francis Bitter. And we were running a 280 gigahertz gyrotron at 10 Tesla, and the Bitter magnet took 32 kiloamps, and it was cooled with 2,000 gallons per minute. And on the flip side, a superconducting magnet like the one here runs off, 208 single phase, 20 amps. It runs at 40 amp power supplies that run at 1 volt because that magnet's superconducting. So you just need to overcome the external connections, sort of. So that's a huge change. And I would call that an enabling technology. So in the past, really since the 80s, large bore high field superconducting magnets became available. So superconductors are obviously being worked on for much bigger applications than gyrotron magnets, but we sort of rode along with the superconducting revolution. And a large bore magnet that has at least a 20 centimeter bore or so, because you have to slide the gyrotron in and you have to have space for all of the cooling, so it has to be actually quite big. This is an enabling technology that really changed gyrotrons in the past 40 years or so. And another one that you can Google is, I've made reference to it, the chemical vapor deposition diamond windows. So on the left is a typical gyrotron window. It's about 3 or 4 inch clear aperture in diameter. And even though it's gray, that's synthetic diamond made with a chemical vapor deposition process. And I can promise you the quarter in that picture is to show you the size. It is not an indication of the price. Back when De Beers company, they're a strange company, I can tell you. They are so weird. But anyway, they were making CVD diamond way back in the 90s. And it was, they had copyright infringement problems in the US, so they weren't allowed to sell here. And you'd have to go to the Isle of Man and bring back diamonds. It was crazy. But back then, a disc for a gyrotron window was $150,000 or so. It's come way down in price because now there's some competition. And De Beers formed a offshoot called Element 6, and they're here in Santa Clara actually making, and a lot of US and European companies make it. But you can Google Diamond is magic material for gyrotrons. First of all, it's really strong. The tensile strength is 350 megapascal or something like that. Also, the thermal conductivity is better than copper, and it's transparent to microwaves. And everywhere from a few gigahertz to a terahertz, it's very low loss. So it's perfect for us. And by the 90s, gyrotrons could actually make more power than the output windows we were using could pass. So people were envisioning all kinds of crazy things like 2 windows out, but then Diamond came along and changed everything. So you can Google it and try to find a YouTube video, but there's this great demonstration where somebody holds the Diamond disc and cuts through ice because the thermal conductivity is so high that the heat of your hand allows you to cut through the ice like a Ginsu knife. That'll be a fun Google. So there are a lot of other things that happened in gyrotrons in the last 20, 30 years, but they're really boring. They're not as fun as superconducting magnets or CVD Diamond. So before I conclude, I would be remiss if I didn't say gyrotrons are not one thing. They're big and small and high frequency and low frequency and amplifiers and oscillators. There are a lot of things. And although fusion was the original application and is certainly the dominant application, it's not the only application. Other things grew up. So like the gyrotron on the right is for a I shouldn't say that at AVS, for a 95 gigahertz radar in Massachusetts, run by the Air Force and MIT. In the center, there's a big fusion gyrotron, and then the Howard Jory, the American father of the gyrotron, is holding a small gyrotron that's used for industrial processing, for ceramic sintering, things like that. And on the left, we use gyrotrons for a nuclear magnetic resonance enhancement tool. It turns out NMR, a great spectroscopic technique, is low signal-to-noise ratio. So there is a technique where you inject just a few watts of a really high frequency made with a gyrotron, and you can increase the signal-to-noise ratio of NMR, and spectra that took, I don't know, 2 months to resolve can be resolved in 5 minutes. So we find all these crazy applications once we have a megawatt CW gyrotron. And really, a gyrotron is not just one thing, it's everything. So I think I'm very close to being on time here. So to summarize, even though we don't always get the best press, the magnetic confinement fusion is doing great, and plasma heating is the backbone of magnetic confinement fusion. It turns out that electron cyclotron resonance heating is the premier method these days for magnetic confinement plasma heating. It tends to be between 30 and 300 gigahertz, depending on the tokamak, and they need tens of megawatts or hundreds of megawatts for their systems. I would say the gyrotron is the obvious or maybe the only choice if you actually want to make a megawatt CW at 200 gigahertz. You do not have a lot of choices. And because we're still going strong, there is worldwide development of gyrotrons going on for fusion heating and for a variety of other applications. So I tried to do it with no equations, and for a general scientific audience, you can tell me later how it went. And I think I could take any questions if there are any. I'm almost exactly on time. Does our moderator, yeah. Little, yeah. Yep. That is 10 kilowatts at 28 gigahertz. He's not holding the magnet. That's just the tube. The magnet weighs another couple 100 pounds. But yeah, 10 kilowatts CW. Mm-hmm. Our moderator. Yes. It's complicated. No. We have a helically cut launcher with special wall perturbations that makes a mode mix so that when it's launched off the launcher, it's a near Gaussian beam. And then we have a series of mirrors inside the gyrotron that both transport and shape. So you can unfold it. If you think of the RF like rays, instead of thinking it like that kaleidograph picture, there's just a whole bunch of rays. If you sort of make the mirrors that it's bouncing on the right shape, you can unwrap those rays and send out the pencil beam. It's complicated, but it works. That's a new invention too in the last 20 years. It's very efficient. And we have to be above 95% because when you're making a megawatt CW, any stray radiation is bad. So you say, oh, it's only 5% stray radiation. That's a lot of power to deal with. So we have to try to be 97, 98% efficient doing that. Fancy machining, I can tell you. Very fancy machining for that. Yep. Yeah, they are really, they are for diagnostics for sure, but they're also for raw heating. So, you know, the modern tokamaks being designed have 100 gyrotrons or so, and it's a gyrotron farm. They always say gyrotron farm, but I'm a city person, so I think it's like a gyrotron, you know, subdivision or something. Yep, lots of gyrotrons.
So in terms of actually using it for commercial
Mm-hmm.
generation,
Ye-
principally power source?
Yep.
Or direct current?
No, it drives a current, but it's not direct current, so it's just to heat, and it does. Mm-hmm.
Boiler for the steam turbine or something.
Mm-hmm. Mm-hmm. Yep.
But lower risk.
Yeah. Yeah. Mm-hmm. Mm-hmm. Oh, they have all kinds of diagnostics for that. I'm not a diagnostic expert, but they get signals out and have all kinds of ways to determine that. Yeah, I wish I knew specifically, but I really don't know how plasma temperature measurements are made in a tokamak. Sorry. See, I said I wasn't an expert at anything, and I meant it. Mm-hmm. Mm-hmm. Oh no, they do their accounting honestly. They even count like the air conditioning in the building. So if they break even, that power thrown away in the gyrotron is included in the calculation. They're very honest. That's why there's no ignition yet in a magnetic confinement fusion. Probably, yeah, probably, but they don't normally do that. They just have cooling loops and, yeah. It probably, you could make the coffee with it probably, or heat your lunch, right? Okay. Thank you.
Update on the order. So thank you again for the wonderful talk. That was very, very informative. I have an update on our speaker list. So let's see. So our first speaker has made it in, but we're going to give him a chance to catch his breath. Literally, that's what we said we're going to do. So we're going to move on to actually our third scheduled speaker, and then after that, we'll go back to our first speaker. Our third scheduled speaker, who's going to be going next, is J.R. Gaines. So J.R. Gaines, he's the Technical Director of Education for Kurt J. Lesker, and over 40 years of experience in materials and vacuum innovations, and has taught at many universities and companies, and today he's going to be talking about neutron-resistant vacuum systems for fusion energy applications. So we're going to get up his talk right now, and we'll turn it over to him, and then afterwards we'll go back to the first scheduled speaker who has arrived, and hope you can catch your breath and get some coffee and use the restroom and get settled. So, all right. So I think, as you probably know, this is the This is a microphone for the room, and then Chris is live streaming, so we want everyone to talk into that.
Thanks, everyone. It's right there. We good? All right. Later that same day, we were ready to go. Well, yeah, thanks, everybody. Again, my name is J.R. Gaines. I'm the Technical Director of Education for the Kurt Lesker Company. I have one of the great jobs in the world in that this wonderful company just sends me around the planet to teach classes on vacuum technology, and I'm excited to be here today to talk about how we might make vacuum chambers a little more resistant to the radiation that these fusion reactors put out. Hey, there's my contact information. If you want a copy of these slides, send me an email and I will send you a PDF of these things. There's my phone number too, but don't ever call me. I never answer my phone unless it's my wife. Hey, as I said, I go around the planet and teach courses. I mean, we have a massive suite of classes that we teach. I mean, this is a session I just did at Oak Ridge to their fusion and plasma people. We also have a bi-weekly webinar series that we do. So, this is free, 1 hour every other Thursday on really useful topics like how to clean things, how to detect leaks in vacuum systems. I mean, good fundamental stuff. Here's what's coming up. I think March 6th, when I get off my airplane, I'm going to do one on cleaning. I'm going to do one in the middle of March on residual gas analysis. Hey, humans have this wonderful superpower. And your superpower is that you can forget. And it's just brilliant. So that if you don't look at these slides again, in 7 days you will forget I was ever here. And that might be important for a lot of you. But if you do remember this stuff, you do need to go back and kind of review the data a little bit every day. That's what I'm going to talk about today. I'm not going to read that to you. Hey, if you've been into my lectures before, I love this graphic. This kind of talks about where vacuum is used in our world. This is pressure down on this axis. This is from this wonderful company, Edwards. It used to be an English company, and they're now Swedish. I think we'll all be Swedish one day. Hey, the big gorilla in the room has always been the semiconductor industry, but if the fusion industry does what it says it's going to do, there'll be enough equipment in the fusion industry to rival what gets spent in semiconductors. I mean, so it's going to grow to be a big industry. So if you think about the clever things that we need to know in order to make great vacuum chambers, I want to add one. It's called neutronics. So we're going to really need to learn how to deal with these neutrons. Again, the previous speaker kind of explained fusion to you, so I won't waste your time on that. Again, just to contrast it with fission, and again, fission's been out there for a long time. We're going to need fission anyway, so get over it. You take a big atom and you split it into some species which are pretty radioactive, and they kind of stay radioactive for 100,000 years or so, as opposed to fusion, where we're going to sort of merge tiny little atoms into something, and by sort of changing the mass, we're going to generate some energy. Again, this goes back to Einstein's fundamental equation. We're going to change m, and so E has to change. You saw this graphic a few minutes ago, isn't that hoot? Hey, this burns me though. So even if we get this wonderful fission reactor going, and I think this is a cartoon maybe of the ITER reactor in France. There's a cartoon person there. All it's going to do at the end of the day is boil water. That just blows my mind that we're going to use all this awesome technology to go out and make water hot. And now, not that this is trivial, and anybody out here who does steam reactors, I really admire what you're doing. This is stainless steel at maybe 400 C and 2,000 PSI. I mean, so this is really pretty robust system here. But your fission or your fusion reactor is just making boiling water. Hey, in terms of vacuum chambers, since we're here to talk about vacuum, the ITER chamber is starting with 10 to minus 7 torr. Generally speaking, tokamaks, smaller ones, are in the 8, sort of right on the edge of ultra-high vacuum. The NIF facility that she mentioned, again, is an ultra-high vacuum. Zap Energy's Z-pinch confinement system, again, ultra-high vacuum. So these are non-trivial vacuum systems, and they're huge, or they can be. Now, in the course of this plasma, again, this is a cross-section of a tokamak, and I'll show you a couple other designs. In this plasma, as that thing gets emitted, there's neutrons that are byproduct of that thing, and those neutrons then go tunneling through the walls of the reactor. And there's some shielding and things like that in there, but your vacuum vessel is still going to see some sort of degradation over time from neutrons. Again, so neutrons are going to come barreling out of our plasma. There's going to be some reaction products. We really won't spend time on those things today. And eventually we get some heat, which goes into the boiling of the water. But again, these neutrons are really aggressive, and so as they go tunneling into the materials, the structural materials that our reactors are made out of, they physically dislodge things. We'll talk about that in a second. Think in terms of penetration depth. For a fusion reactor versus a fission, fusion is in the dark color here. There's a couple of inches in steel. There's 15 centimeters through aluminum. Again, these things really are going a long way. Here's some images from ITER. Again, our engineering team was in there just a couple weeks ago and took some of these images. I mean, that is a vacuum chamber. That's part of the vacuum system, and you can see that it's going to have several lobes as they fill this whole thing out. And so this is a really, really exotic system. And I think it was made by several different manufacturers from all over the world and then shipped to France and assembled, and of course it didn't fit. Well, I think they fixed it on the floor. But again, as I said, as a neutron goes into your structure, the crystalline structure of your steels, it can create voids. It can create interstitials where maybe you've got a molecule which is not where it's supposed to be. Let me just talk about how they measure radiation damage over time. We talk about a thing which is dislocations per atom. So imagine you've got a piece of steel which has got a whole bunch of atoms in it, and over the course of its life, those atoms are going to get moved. And in a fission reactor, they get moved about 10 times over maybe a 30-year useful life. And again, it's a cumulative measure of radiation damage. And so your ITER reactors, your current fission reactors are sort of down in the sort of 10 displacements per atom over their lifetime. Fusion reactors are now up at around 150 displacements per atom over a 5-year period, not a 30-year period, but a 5-year period. Okay, so the lifetimes are much, much shorter. The damage is much, much more severe. And even at small doses, even at small displacements per atom, you see radiation hardening. You see the metals get brittle. With more damage, sort of beyond what you would normally see in the lifetime of a fission reactor, you start getting precipitates or transmutated materials inside the steel, so that some of the components of steel, I don't know if you guys are metal experts, but some of those things, when you hit them with a neutron, become other things. Titanium becomes other kinds of species, and that starts to mess with the structure of your steel so that it starts to change dimensions, and it might swell. And then over time, if you have a really extreme amount of radiation damage there, some of this stuff turns into gases. So now we've got helium pockets and things like that along the grain boundaries of your steel. And so you can imagine things like structural performance, thermal conductivity, all of these wonderful properties that you love about steel start to go to heck. So again, fusion reactors, again, we love them. They're around for long, long times. You see about 10 displacements per atom over 30 years. Fusions now are happening over 5 years. Now, the good news is, as the previous speaker mentioned, 5 years is a long time, 158 million seconds, and the world's record, actually it's been bested since the East work, is now 1,300 seconds, or about 22 minutes. And so, the people that are designing these reactors, when I go to them and say, hey, are you worried about your materials? Right now they're just trying to get from 1,300 seconds to some number like that. So again, they've got some work to do to sort of get to full capacity. Again, these are the kinds of things that happen to metals. I won't bore you by reading your slide. But just keep in mind that for a fusion reactor with this sort of displacements over a 5-year period, you're going to see swelling of like 10%. Imagine you've designed something in sort of millimeters or microns, and then it grows by 10%. Just all sorts of drastic reductions in these properties that we love about steel. And again, just look at these damages. I mean, this is really, really bad news. And again, I'm showing you a tokamak again. There's other designs out there. There's just certain regions of the tokamak where this plasma gets, or where the neutrons sort of get concentrated, and you see the most damage. Again, this is just a cartoon of the NIF, a reactor that she mentioned earlier. It was the first one to sort of go positive, where the amount of energy going in was less than the amount of energy coming out. But again, there's other designs here. Again, you can imagine that everybody's just trying to use some kind of a tool to apply the pressure that you need to create fusion. OpenStar, I think this is in New Zealand, right? These guys are going to physically hang a magnet in a vacuum chamber, superconductive magnet floating in a vacuum chamber. What could go wrong? Stellators, again, just really, really complicated structures here. I mean, controlling this plasma is apparently quite exciting. This is the Z-pinch fusion reactor. These guys are clients of ours, and happy to say we've made vacuum chambers for their reactors. A little different design, where they're going to sort of anode, cathode, similar to the sort of arrangement we saw in the previous presentation. They're going to arc this into a liquid anode. Very cool. And then their neutrons, I think, go out to the sides. They just published some really nice work. This is from Rachel Ryan and the group at ZAP, where the idea was they wanted to understand where the neutrons were going. Were they sort of going out radially in all directions, or were they sort of focused? And obviously, in terms of neutron damage, we really would love to have our neutrons sort of radially focused, as opposed to just sort of going into one part of the reactor. Hey, look at the inside of this reactor. Look at this. These are armored tiles. These are tungsten, as it turns out. Doesn't this look like something you would drive into on a battlefield with? I mean, this is really, really aggressive, right? Because the environment there is absolutely incredible. I mean, for those of you, here at the Vacuum Society, if we talk about sputtering, for those of you that sputter, you know that that's a great way to deposit material, a great way to etch things. And so right at that wall, right at these plasma-facing surfaces here, you see sputtering going on. And sublimation, all kinds of bad acting going on there. These are relatively closed cycle systems, so you do see some redeposition, but that tungsten surface is being continuously eroded. I mean, you're seeing this kind of damage here. Here, look at the temperature. This got so hot, obviously, that it melted and then recrystallized. I mean, really, we're talking about extreme temperatures, and there's a lot of work going on just to try to keep the plasma away from the walls of the reactor. Again, sublimation due to heat, this is in molecules per square centimeters per second. That's the rate at which things are just coming off the walls, and you have physical sputtering going on at the same time. So, I mean, these are really pretty robust rates, and if you're trying to make a gold film on a microscope slide, you'd be pretty happy with these kind of rates. Again, so again, just not to dwell on this too much, but depending on how much radiation you have, very, very low levels, you might take something which is crystalline and make it amorphous. At really, really high levels, you're going to see things like helium gas forming at grain boundaries. I mean, so this is really, really exotic stuff. So what are we going to do? How are we going to sort of let fusion reactors grow up and become useful? Again, this is bad, right? So if your steel is going to get, if it's going to change dimensions, if it's going to have holes in it, bad stuff's going to happen. Obviously, everything wants to leak. So what can we do? What's been going on for the last couple of years, there's been some interesting progress on new steels. Ways to alter traditional 304 or 316 type stainless steels so that they are more robust. I'll talk a little bit about self-healing materials. There's some things that we can do to actually make certainly ceramic tiles, for example, that will actually heal themselves. And then I'll talk a little bit about coatings. And since we're at the AVS, that should be a hot topic for y'all. Again, what we've seen in terms of steels, again, here are just a couple of popular steels that have been out there. The Europeans have been kind of leading the way. Eurofer 97 is a steel alloy that I'll talk about a little bit. What they've done to make this sort of less susceptible to neutrons is they've tried to remove some of the actors that are in steel that are actually sort of magnets for neutrons, with the idea that with all the sort of side reactions that occur in the fusion reactor, that the thing's sort of cool enough that you can actually handle it within a lifetime or so. Again, back at my shop in Pittsburgh, most of our chambers are made out of 304L or 316L, very well cooked out technology. You can put everything together with a TIG torch, or you can do it in atmospheric conditions. You're welding on the inside of the chamber, obviously, trying to make a nice vacuum barrier. Here's just some data for you. This is, let's see, this is data from China. So these are a couple of different versions of a steel that was made in China, and you can see that in terms of neutron resistance, that certainly the CNS1 is not as quite good as the CNS2, and I think the difference there is what they removed titanium. They changed some of the concentrations of some of these bad actors, but you can see even with high doses of neutron radiation, you still see sort of transitions in the crystal structure. You still see the beginning of some voids and other species there. I'm so sorry that you can hardly read this, but if you ask me for the slides, you can study this at your leisure. I've tried to mark the things in green where they've tried to reduce some of the traditional content in steel, and then some things here in red where they've actually added some things back, things like tungsten, things like vanadium, things like boron. These are really, really great actors in terms of blocking or sort of being tolerant to radiation. Again, this is too busy, this slide. I'm sorry. I hate to read stuff like that. Again, another metal that was just recently produced in the UK, and they actually made a bunch of it. They made 5.5 tons of this stuff called Neuron. It's also going to be one of the steels where they sort of reduce some contamination in there. Again, this is just some pretty pictures of them. The sort of first 5.5 tons of this steel rolling out of a shop in Manchester, I think, England. I'm desperately trying to get a hold of some of this stuff because I want to try to weld it or put holes in it. Again, Eagle Pitcher's also done some nice work if you need to work in aluminum. There's a couple of aluminum alloys which have been with some boron additions to them, which make them a little bit more robust if you need aluminum. Again, years ago, even after Kurt bought my company, I was making shielding tiles for the spallation neutron source at Oak Ridge. Turns out if you have a really neat isotope, a +6 isotope of lithium, that's a fantastic shield for neutrons. And the lab would, I'm a battery guy. I make a lot of solid-state battery materials. And this happens to be the electrolyte for a solid-state thin-film battery. And so the lab got a hold of me, and they would ship me this really neat lithium +6 isotope as carbonates, and I would convert it to lithium orthophosphate and then make it into what looked like subway tiles. And they would then go back and tile up their instruments at the spallation neutron source with that. It was a great gig. Now, I have also done self-healing ceramics. And I worked with Nanophase Technology years ago, and we made ballistic armor, flak jackets, things you could wear that would stop a bullet. And I think the quality control was that we had to stop 2 bullets. And not while we was wearing it. I mean, we did that in a lab somewhere. But the idea is with nano additions, and I think we were making, adding sort of nanocrystalline alumina to these tiles, when a crack would form and it would get to that nanocrystalline alumina, it would stop. So this thing would do this cracks. Even if a bullet was cracking a tile, it would only crack it a little bit so that you could survive a couple of shots. There's also some really neat work going on with tungsten. Tungsten as a structural material is not so great. It's made from powders. I mean, it's just kind of a tough thing to work with. But by adding in some sort of nanoparticle ceramics to it, you can make some really, really interesting materials. And the ceramics add is, again, crack stopping devices. They're also sort of centers where the neutron damage can be concentrated. And again, this is just how it's done. You sort of mix powders together, put it into some kind of encapsulation, roll it. This is my old rolling mill back at Superconductive Components. It's really neat, though. If you do the rolling correctly, you can actually make a ceramic tungsten structure which mimics the structure of pearls. Pearls are awesome. If you cut your wife's pearl in half, you're probably going to be in a lot of trouble. But with a microscope, you can see this really lovely brick-type structure. I mean, like a brick wall. And so these things are really, really robust. They can withstand a lot of temperature differentials, a lot of real damage there. So we can make a sort of a pearl-like structure by rolling tungsten correctly. Again, and by that we can make foils now, multi-layer foils, and this one happens to be tungsten with the silver composite there. Again, let me just talk to you for a second about shielding materials. I don't know, where am I at time-wise? Am I okay? So as I mentioned, again, this is a pretty picture of a tokamak. In these regions up here, that's sort of where the neutron damage tends to get concentrated. And so there's really some lovely work going on using tungsten and tungsten-coated Inconel. So Inconel is a lovely high-temperature substrate, and you can put tungsten coatings on it and actually tile up these areas here of the tokamak where you're going to see some of this damage. And again, this is just some work done. Again, that's your Inconel substrate. This is about, I want to say 20 or 30 microns of just pure tungsten. And works well as a shield. Of course, there's now a sort of intergrade tungsten. And this is a super grade of tungsten, which has been where the carbon's less. I mean, all of these things are sort of in better, higher purities than you would normally see in typical tungsten. Things like nickel, which is sort of a bad actor, silicon, kind of a bad actor. So again, let me, if you're familiar with HiPEMs now, again, a lovely, lovely coating process which lets you make sort of arbitrarily thick films. These are multi-layer films made by a client of ours at the Royal Institute in Stockholm. These guys are actually making cutting tools, and so this is 150 microns of a coating on a cutting tool that sort of doubled the life of the cutting tool. Using HiPEMs, again, this is a lovely process. If you're not familiar with it, you can actually sputter with the material that you're actually trying to do your coating with. Again, multi-layer coatings, you can stack things up. Think about your optical coatings that you make. These things where you can do sort of reflective layers, absorptive layers, things that polarize, structural materials. Again, I just did some calculations on sort of what a decent shield stack would have to be. That's about 251 microns. You're probably thinking that's not a thin film anymore. I agree. But you can do that with HiPEMs and with sputtering. Well, maybe not. Some of the HiPEMs really does like things to be electrically conductive. We also see a lot of nice work now, sort of alternating metal layers with organic material. I mean, if you're familiar with the sealing technology that's used for organic light-emitting diodes, that's all titanium and organic multi-layers. Again, unfortunately, what we don't know yet is how we're going to actually join some of these things together, how we're going to weld things together to make nice chambers. I'm assuming that we can't actually use our traditional welding techniques. People are investigating things like stir friction welding. This is really a neat technology which can be done at atmosphere. No heating required. You use a special sort of a tool here which is going to rotate like a very, very high speed, and as it bangs into the two pieces that you want to join together, it creates some sort of pool of molten metal right at that intersection there. And if you do the right speeds and feeds, you can sort of make a credible vacuum barrier. Also, people are talking about diffusion welding, where we would take two pieces of material, put in some kind of a goo in the middle, heat it all up under pressure, and form your joint that way as these things sort of diffuse across a barrier and make your vacuum joint that way. I think that's hard. That sounds to me like a real tough way to make a vacuum chamber. I'm not voting for that one. Now, this I really, really love. This is the result of printing. Right, 3D or additive manufacturing, using these really wonderful sort of chemical compositions of this sort of fusion-resistant type steel. What I love about this is that I think with additive manufacturing, you can actually influence the grain orientation of the things that you're putting down so that you can make an oriented film, and I believe that those oriented films may be even more robust than just sort of the bulk materials there. Again, so just keep in mind, again, neutron damage for fusion is going to be much more aggressive than what we see with fission. These materials that I'm talking about can also be used to refit existing fission reactors. It's all good. You're going to see, I didn't come here to talk about fission, but you're going to see a lot of these sort of now small fission reactors, sort of neighborhood-sized things that'll do a couple 100,000 houses, where their fission reactor is more like a battery. Those things will be made from these new materials. Again, I'm trying to get some samples of these metal alloys so we can do some of the fundamental works, like can we weld it, can we drill holes in it, that sort of thing. There's lots of films and foils that can be made. Again, a huge fan of printing here. Again, that's my contact information. Again, if you want a copy of the slides, I'm happy to send it to you. Any questions from anybody? Yeah. Thank you. Yes, sir. Oh, yeah. Oh, I'm assuming they're going to be pretty hot. Meaning it'll be like a decade before they're cool enough that you can touch things with your hands. Okay, I mean, so you could probably get to them with some protective clothing on, that sort of thing. But think about 10 years before you sort of get down to the sort of the natural radioactivity of uranium oxide that you find in the ground. Okay. Other questions? I put you to sleep. Yes, sir.
I think you said that silicon is a bad actor.
I think so.
And also, I assume that carbon would be, I mean, it's a neutron absorbent.
Yeah.
So then you said silicon carbide together seems to be a good material. Silicon carbide.
Yeah, and I'm not quite sure about that. I mean, when I was doing my lithium orthophosphate, tiles for these guys, they were replacing silicon carbide tiles with the stuff that I made. So it's used. I think it's the carbon, as you mentioned, the absorption piece of the carbon, and the fact that silicon carbide is really fantastic at 2000 C. I mean, it's just such a wonderful material at those really horrible temperatures. But again, they were looking for alternatives. I mean, so that's why they came to me. Okay, yes, sir.
I have sort of a question about the lithium tiles. Would you include this with rubidium, or would you like to both as sacrificial?
Oh, yeah. So I'm not sure I got your question, but you wanted to know if the lithium was sacrificial, if it was really kind of part of the process.
Yeah, the lithium is by neutrons into two buildings.
Well, yeah, but so I don't want to confuse you. So lithium is used in a fusion reactor to help create the tritium, I think, that you need. I mean, it's somehow in the fuel cycle there. Again, I'm not an expert there, but so the tiles I was making were not sacrificial. They were simply shields, and they were supposed to stay stoichiometric forever. Okay, so they were not part of that the reaction that is occurring right at that plasma interface. And that's where you're seeing lithium converted into other things. Different source. Other questions? Great, good. Thank you so much, and invite me back. Do you want to use my laser pointer?
Oh,
Or are you
I
done?
think Sol may want to use it. See, I'm just going to show. Oh, Sol's going to be next. I'm going to just show the schedule real quick. Yeah. Right. Yeah. You have to. Okay. All right. So yeah, thanks. So yeah, as you know, there was some. Let me get the mic real quick. Which one? Check. Is it this one? Oh, it is working. Okay. Check. Yeah. So as you know, there was some traffic on the 101 and he's an overturned truck. So we're happy to have our first scheduled speaker, Sol Olavaria, come in and present now before we go off to our lunch break. So Sol is he joined the ALS about a decade ago, right? And he came in from the UK, where he was at the Joint European Torus Fusion Energy Lab in Oxfordshire. Right? Prior to that, he worked over at Diamond Light 6 Source for 6 years, doing vacuum engineering and beamline design. And today he's going to be coming in and talking about the ALS accelerator systems and the project status update. So we're really happy to have you, and I'm glad you're able to make it here safely, and I hope you had a chance to catch your breath before you give a talk. So thank you so much for being here. So I'll turn it over to you. Yeah, there you go. All right, thanks.
still morning, but thanks for the opportunity to present. I was stuck in traffic this morning. Glad I was able to make it. Oh, okay.
How did you do this with your screen before?
Okay, thank you. As has been said, I come from Lawrence Berkeley Lab, and we're working on the upgrade of the ALS, which is the Advanced Light Source. This is not a fusion talk, but you'd agree with me that one of the primary challenges for fusion is material science. There's no better place to study material than accelerators or free electron lasers. And this is an upgrade that we've been working on for a few years. My background is vacuum engineering, which is why I'm here, but most of this talk is actually project management update in nature, so you'd have to bear with me. So the ALSU project promises to deliver a world-leading light source that provides users with bright, highly coherent flux, mainly in the soft X-ray regime. So we're looking for diffraction limits at around 1.5 keV. However, we do have a couple of tricks that we could play that actually allows us to get to the high energy regime as well. The way we achieve this is by basically taking out our current accelerator and replacing it with a new one. So in the top image, you see what ALS looks like today in terms of the accelerator. It has a storage ring, and the profile of the beam, as you can see, is this pancake shape. And the hope with the upgrade is to get it into this kind of laser-like shape. Doing so, we increase the brightness. We also increase the coherence with a focus at about 1 keV, as I mentioned. And we're going to develop new experimental capabilities that allows us to leverage this optimized source that we're going to get from the upgraded accelerator. As I mentioned already, we have a couple of tricks that we play to get into the hard X-ray regime, and also we do have 2 or 3 beam lines that focuses in the infrared regime. So the science case for the upgrade is already well made, and ALS has had incredible success over the last 30 years, producing a number of Nobel Prizes. Most recently, you recall Jennifer with the CRISPR project, and also most recently David Baker. And the focus of this, the researches that we perform ranges from condensed matter research to biosciences to more energy-focused research. And as I mentioned already, for fusion, the challenge really that is remaining is material science, and facilities like this are absolutely essential to overcoming those challenges. And we're looking to upgrade our machine to position it in a place to help address the emerging national, global research needs as we move forward. As I mentioned, the way we do this is to remove our current storage ring, which is a triple band Acromat. You can see the lattice in the right-hand side there, and we're going to replace it with a 9-band Acromat. The way to increase brightness and coherence is well established. It's to do with the amount of magnets you have in a unit space, and by doing so, you have greater control over the electrons. Therefore, you can make them more coherent, and you can exploit diffraction limitations such that the electron has a diffraction property that is better than the photons that you actually achieve from those electrons. Our machine is quite small. It's a 200 meter circumference machine. It's operating about 2 GeV of electrons at 500 milliamps. And you can see the incremental improvements that we've made in the amount of photons that we produce per unit space over the last few years. And we're really looking to make, if you like, a big leap in improving the source. And that is what this project is about. The scope of the project involves replacing the existing storage ring with 2 new rings. The first ring we call the accumulator ring. It's essentially part of the injection system, and we're going to commission the accumulator ring whilst the existing storage ring is still operating, and in fact, we're in the process of installing the accumulator ring right now. You can see it on the picture on the lower left. This is a picture of the accumulator ring a few days ago, where the inner wall of the storage ring tunnel used to be bare. Now it has this accumulator ring hanging about 6 feet up in the air, and we're almost finished installing all the mechanical modules, and very soon we're going to move into commissioning the accumulator ring whilst the storage ring is still operating. Then in a few years from now, we're going to replace the existing storage ring with a new ring. The design and procurement of the new ring is ongoing. The plan is to shut down the facility for a year. The first 3 months will be spent removing the existing machine, and the final few months spent installing the new machine. In addition to installing the 2 new rings, we're going to have transfer lines that connects the 2 rings together. We call them the accumulator ring to storage ring transfer line, and the storage ring to accumulator ring transfer line. I should say that the injection system is now based on recovering electrons that were previously used in the storage ring, but now it's depleted in energy, and we put that back in. And the team is working hard right now to complete the installation of the accumulator ring with the intent to commission it within the next year, and then we move into the storage ring installation phase. So this is the sequence of events right now, where, as I mentioned, in the phase of installing the accumulator ring. Very soon we start to commission, then we go into the dark time when the entire facility is shut down. The first few months is spent removing the existing storage ring, then we install the new storage ring, we install the new transfer lines, the insertion devices are installed, and then we move into commissioning of the new storage ring. I should say right now the timing of this event is somewhat uncertain. We're facing a lot of technical challenges that relates to a highly congested old building and facility. Parts of this building is 90 years old. So every time we try to remove something, we uncover new problems that we need to solve. Of course, living in the Bay Area, there's seismic challenges that we have to address as well. And this is taking a toll on the timeline of the project, such that the exact timing of our dark time as of this moment is somewhat uncertain, but we believe that would happen within the next couple of years. This is a better picture of the accumulator ring as it stands today. It's a very gratifying picture because I've had the privilege to live through the design from early concept to being realized with a lot of the modules now installed on the wall. And in fact, I should say, as I'm presenting, I look back there, I see some of the technicians that are actually doing the installation work sitting at the back there. Those guys are great. They work really hard to work in this very challenging environment. Most of the colorful objects that you see, of course, the magnets. The vacuum is so small you cannot see it in this picture. It's buried deep within the magnets. And you can see that we have to remove the roof blocks above the accelerator tunnel to lower in modules of the accumulator ring that's been pre-assembled in a different building and brought into the accelerator complex, because of course time on the machine is a premium, so we as much as possible try to pre-assemble, pre-test modules before they ever come into the accelerator complex with the intent of reducing the amount of installation time, because we want to keep providing users with photons that they need to do the great science that they're doing. This picture kind of illustrates a typical challenge for a complex project like this, in that the mechanical system tends to get a lot of attention in the early days, but the electrical system and the control system tends to lag behind, and that is exactly where we find ourselves with a project. You know, you can have a brand new accelerator, new magnets, new vacuum, new support system, but if you don't have the electrical infrastructure to make everything work, you've got nothing basically. So this is one of the challenges that the project is encountering right now, and we're trying to overcome. Some of the challenges relates to you know, a lot of the electrical system have to meet new codes that weren't existent when the original machine was installed. So if you touch it, you have to bring it up to code. And that is a rigorous, laborious process that could impact the project in a very direct way, because you need permissions, or you need electrical safety officers to approve your cabling and the routing of your cabling and the density of your wireways before you can lay those cables, and that is one of the challenges that we're facing right now. We're starting to overcome those challenges, and the electrical infrastructure upgrade is starting to pick up pace, and the hope is that as we complete the mechanical installation, the electrical will catch up sometime before the end of this year, and we can start to do the commissioning towards the end of this year, beginning of next year. So that is the accumulator ring, and that's kind of where we are as of right now. So looking forward, as I mentioned, we've worked on the design of the storage ring. And again, the design has to be modular, in that we need to be able to install the entire storage ring in a 6-month period, which means all the modules that goes into the storage ring has to be pre-assembled in a different building, tested, partially commissioned, and then we bring them into the tunnel during the dark time to connect them all together and get the machine back into the commissioning phase. I show a cross-section of the key systems, which is basically the magnets, the vacuum, and the support, for which I'm the technical lead. As you can see, the vacuum chambers are rather small. As I mentioned, you can't really see them in the forest of these colorful magnets that you see, but they are there. This vacuum system doesn't rely on conventional pumping. It relies primarily on non-evaporable getters on the inside wall of these chambers to achieve the vacuum levels that is necessary to operate the machine. And the vacuum level that we're looking for in this machine is about 1 × 10⁻⁹ torr. So taking a closer look at one of those modules, you can see it's very busy. It includes the magnets, as I've mentioned, the vacuum, the support system, the cooling system, the electrical system, the control system. A lot of this is being fabricated as we speak, and I focus again on my area, so you can see images of some of the first article magnets for the storage ring being delivered and measured at our facility, and you can see some of the pictures of magnet poles and yokes now being machined at various vendors around the world. The vacuum chambers is also starting to ramp up in their production. You can see a couple of the vacuum chambers completing fabrication and being inspected. The support system, which is this raft that you see that bears the magnets, those are also being fabricated, and we're starting to receive the first units of this so that we can test them and retire any remaining technical risks before we move into full production phase with these components. We're getting components from all around the world, ranging from a lot of vendors in the US, in Europe, in Japan. We have about $50 million of contracts that's been awarded just for the mechanical systems. In other words, the magnets, the vacuum, and the supports, spanning 7 countries and 30 vendors. So right now we spend a lot of our time managing these vendors, so early mornings, late evenings, depending on the time zone, to keep tabs with the production work at the vendor sites. But it's starting to pick up pace, and we're encouraged that by the end of this year, we would be at peak production phase for the components that we need for the new storage ring. Of course, once all those components are delivered, we need to assemble them, and we're starting to plan how that works. You can see this is kind of a bill of material of the components that makes one module, and we need to produce 48 of these modules. It includes, as I mentioned already, the vacuum components, bin diagnostics components, electrical components, the magnets themselves, the cabling, the lifting structures that supports putting on the magnets on the raft and removing them. So there's a lot of effort that goes into being able to assemble one of these modules. Literally, one of those modules contains thousands of parts. So it's a huge logistical effort that the team is currently planning. And part of the challenge we face is whose idea is it to put a lab on the side of a hill in Berkeley? You know, this picture is deceiving because it paints a picture that the lab is on a flat ground. It's actually not. It's on the side of a hill, and in fact, the entire lab is sliding towards downtown Berkeley about 1 millimeter every year. So in a few hundred years, we may be in Berkeley. But anyway, the point here is that assembly space to put up complex machines like this is really lacking at the hill, which means we need to move around, and we have a complex logistical workflow where things have to be moved from one building to another to be able to achieve the assembly work. And you can see this complex workflow that our teams are currently developing that shows how parts and components move from one place to the other. So it's the engineering challenge, but it's also the logistical challenge of bringing together an complex accelerator like this within the confines of the lab. Some of the spaces are taking shape. We have a pre-assembly hall that's been put up within the last couple of years. That picture is somewhat deceiving because if you look at it right now, it's full of boxes and equipment as we gear up. We have our magnetic measurement facility up and running. Our vacuum assembly space is up and running. So the preparation work to assemble the storage ring and get ready for dark time is really well underway. There are significant challenges that we're facing. Some of them I've already mentioned with the electrical systems, but also with just the challenge of trying to bring a 90-year-old building into compliance seismically, electrically, and in all other ways that wasn't existing 90 years ago when the building was put together. So our schedule, our timeline for the project somewhat is uncertain at this moment, but we are working hard to understand those specific challenges and get our hands around them so that we can turn things around and have a more predictable timeline, because our users, they want to know when the machine will come back up as we go into the dark time, and we want to continue the great science that the facility has been doing over the last 30 years. Of course, it takes a team, and this is a picture of I think the team maybe a few years old now. This includes the operations team on the accelerator and also the upgrade design team working hard to realize this machine. I have to spend some time to advertise AVS 71. This is the National Symposium. It's coming up later this year in Charlotte, North Carolina. The abstract submission is now open. So please submit your abstracts. You can see the different topics that are covered national. Why am I bringing this up? I'm currently the program chair for the Vacuum Technology Division for this symposium. So we're looking forward to seeing you there and to submit your abstract in the coming weeks. I think the abstract submission closes 1st of April. So that is the end of my talk. Thank you for your time. So these machines have a lifetime of about 30 years. It's typically the timeline for a major upgrade on facilities like this. So in the U.S., for instance, you can think about APS, Argonne National Lab. They have a similar user facility. They've just completed an upgrade, and SLS2 is looking forward to an upgrade coming up. But what happens is between those major upgrades, there's sort of incremental upgrades, which costs less, and it's more focused on specific experimental capabilities. But every now and again, you have to rip out the heart of the machine, which is the accelerator, and put in a new one, just because the technology has moved on. The expectation right now is that we will go into dark time in about a year and a half to 2 years from now. And after that, of course, we would have a soft start. Maybe for the first year, we may not get the beam currents to more than 25 milliamps, because it takes a huge effort to get such a complex system to steady state operation. But the expectation is that within a year after that, we would be back at 500 milliamps, full performance criteria being met, and hopefully start to realize the promise of the project in terms of the greater performance that enables new science maybe in another 4 years from now. Thank you for waiting.
Yeah, in fact, so I have a very quick announcement for you to rest of today. Okay, so check, just on. Check. Okay, so a few quick announcements is lunch is scheduled from 12 to 1:30. So I encourage you all to have an opportunity to, before that, even go into the exhibition hall. It should be the lunch should be over in the exhibition hall. So please have a chance to visit the exhibitors. We're going to have the afternoon session starting at 1:30 p.m. in this room, and we've got sessions from 1:30 to 3. And on the schedule, we do have it say 3 to 5 p.m. It says wine, beer, and appetizers. But I do have a couple students who are going to be presenting some posters on their PhD work. So we'll either have it out there in the hall, but I'm going to try to move it over into the exhibition room so that you can also have an opportunity to have wine, beer, and appetizers while you're meeting with the students. So that's kind of the plan for today. So please do enjoy what's going on next door, and we'll reconvene here at 1:30 p.m. Okay, thank you.